Welcome to Algebra 2, Unit 0, Section 2, Linear Function Transformations and Systems. So we're going to start off by talking about what a family of functions is. So let's start off here with a family of functions. Is a set of functions whose graphs have basic characteristics in common. Okay, so they all kind of look the same. You have all your linear functions, they all kind of look the same. They're all straight lines. You may remember quadratic functions. They are shaped where they open upward or they open downward. Some of them open up, some of them open down. Some of them are wide, some of them are thin. But they all essentially have the same sort of shape. Well, all linear functions they form a family because all their graphs have the basic same shape. And we just mentioned that that shape is a line. Okay? Well, since we're talking about a family of functions, it would make sense that we have something that's called a parent function. And basically what a parent function is the most basic function in a family. So for linear graphs or linear functions, we have a linear parent function, and it is notated by y equals x, or f of x equals x, because f of x and y can be used interchangeably in these cases. So when you have this function y equals x, our slope is 1 and our y-intercept is 0. So it goes through the origin. Now, if we were to take that linear parent function, kind of our starting function, and we were to change it, changing a graph or changing a function in position or size is called the transformation. All right, so let's talk a little bit about a linear transformation. And it can be transformed in one of three ways. The first of which is a translation. So it sounds a little like transformation, but it's a little bit different word. It's translation. You can also have rotation. And you can also have reflection. So let's talk about what each of three of these mean. Well, a translation is a transformation that moves every point in the same distance, that moves every point the same distance in the same direction. So with this type of transformation, we basically have a graph that's not going to change how it looks, it's just going to change where it's located on the graph. It's going to change where it's located in relation to the x and y axis. And we'll go into more detail on all three of these here in a moment. Now, a rotation is exactly what it sounds like. A rotation is a transformation about a point. Okay, so you're going to pick some point and the graph will get rotated around that point or about that point. And then finally, a reflection. It too behaves very similarly to how it sounds. A reflection is a transformation across a line that produces a mirror image. Okay? So let's talk about all three of these in a little bit more detail. Let's start off by talking about translations, okay? and specifically a vertical translation of a linear function. So here I have a couple of graphs, and I've begun with our parent function. And remember, our parent function is y equals x. So our slope is 1, so you can see we're going diagonally across all of our grid boxes. And our y-intercept 0, which means we are going through the origin. All right, so since this is our parent function, this is y equals x. In fact, let me do this in black so it matches up with the color, y equals x, and I'll go ahead and label it over here as well. All right, let's talk about if we were to translate this function. Okay, so let's say I want the graph y equals x plus 6. Okay, well, x plus 6 is a translation. So here is the definition specifically of what happens when you have a vertical translation of a linear function. When the y-intercept is changed in the function at y equals mx plus b, the graph is translated vertically. So if b increases, the graph goes up. If b decreases, the graph goes down. So here we have increased our y. We've increased it, our y-intercept. We've increased it from 0 to 6. So our new y-intercept is y equals 6. So it's 1, 2, 3, 4, 5, 6. So here's our new y-intercept. And then we can find our slope is 1 over 1. So we have the same slope. So we go up 1 over 1, up 1 over 1, up 1 over 1. And I'm just going to plot over here on this end, and I'm going to follow our line diagonally over the other way, and I'm going to plot over on this end, and now I'm going to at least attempt to plot our line here. Okay, so I've got everything set up, color is correct, so let us see if we can plot this. And so this would be our translated line. Let me maybe do it from here to here. There we go. So this would be our translated function, okay? And our translated function was translated up by 6 units because we went from y equals 0 to y equals 6. So the translation occurred upward, like, oops. Let me do it this way. It was upward here and upward here, and you could draw those arrows really anywhere. It was translated upward. So the way we would notate that is we have a graph that was translated up 6 units. Okay, well, let's take a look at another type of function, okay? What if we had, instead of plus 6, what if we had minus 6? Okay, so here again we start with our parent function, y equals x, and now let's translate it down by 6. So let's say we want to do y equals x minus 6. Okay, well, we can do that. And we're going to do that by going 6 units down on the x-axis, or I should say y-axis. So let's follow this down. 1, 2, 3, 4, 5, 6. So there's our y-intercept. Okay. Now we're going to follow our slope, which is still 1. So rise 1, run 1, rise 1, run 1. And we're essentially going diagonally across all of our grid boxes. Okay. So we'll end up over here. And then on this end, we're going to end up over here. So now let's plot that line. Okay? So what we've just done is we have translated the graph downward by 6 units. And again, it's 6 units because we went down along the y-axis by 6 units. 1, 2, 3, 4, 5, 6. You can count that anywhere along this graph. 1, 2, 3, 4, 5, 6. So we will say that this graph was translated down 6 units. Okay, let's talk about the other types of transformations. Let's go to rotation. Okay? So here we are, we're starting with our parent function again, y equals x. And we are going to now rotate. So how do we rotate a linear function? Well, when the slope is changed in the function, y equals mx plus b, it causes a rotation of the graph about a point 0, b being our y-intercept, which changes the line's steepness. Okay? And because we change the line's steepness, we essentially make it look like it rotated. So let us take a look at what happens when we change the value of our slope. Now, notice I'm saying value. You have to be very careful here because if we change the sign of our slope, make it go from positive to negative, that's going to do something else for us. What we're simply talking about is the value. So right now our slope is 1. Let's see what happens if we were to make our slope 2. Okay, so we're going to plot the line y equals 2x. Well, our y-intercept is still 0. So we can start our graph right here at the origin. Now we are going to take our new slope, which is 2. So that means we are rising 2 and running 1. Rising 2, run 1. And I'm just going to follow this pretty much to almost the end of the graph here. We're also going in the other direction, down 1, down 2, and backwards 1, down 2, backwards 1. And you can do that and follow that through the graph pretty much to the end. And if you had a ruler, you could connect those 3 dots. If you want to plot along each step of the slope to connect your dots, that's perfectly okay as well. But what I have is essentially like a ruler because I have this nifty device that will allow me to draw it straight. And there's our new line. So what essentially happened was we ended up with a graph that looked like it rotated this way on the top and this way on the bottom. So if we have a graph that looks like it rotated like this, it looks like it's rotating counterclockwise. And since it looks like it rotated counterclockwise, we say that it rotated counterclockwise about, because we need to know where the rotation occurred, about the origin, or 0, 0. Because you'll notice that that is where we have a point in common, where our parent graph and our new graph cross each other, is right there at the origin. Okay, and our rotated function is this y equals 2x. Okay, so now let's see what happens if we say, instead of augmented our slope, which means we increased it, what if we diminished our slope or kind of decreased the value or made the value smaller? So we're starting with our parent function once again, y equals x. But now, instead of making it bigger and making it 2, why don't we make it smaller and say that we have a function y equals 1/2 x. Okay, so we made our slope smaller. We made it half the size. So again, our y-intercept is 0. And now we're going to plot our rise over run, but this time our rise over run is up 1 and over 2, up 1 and over 2, up 1 and over 2. And we're just going to follow that until we get pretty close to the end here, okay? And now let's go the other direction, down 1, back 2, down 1, back 2, and we're going to follow that all the way until we get to almost the end of our graph. And now let's see about graphing it. So we'll go here and we'll follow all the way through to here. So now we have our new graph, y equals 1/2 x. So now it looks like it's rotated the other way. It looks like we had a rotation here and a rotation here. All we really did was change the steepness of the line, but it does give it the appearance that it rotated, which is why this transformation is called rotation. And this one we can say that it was rotated clockwise. And again, about 0, 0. Because that's where the rotation occurred. Okay, so now we've talked about what happens when we change the y-intercept. We've changed the value of the slope. So finally, let's talk about what happens when we change the sign of our slope. And in this one, we're talking about reflection of a linear function. When the slope m is multiplied by -1, which means we're changing the sign of our slope, the graph is reflected across the y-axis. So, for one more time, we are starting with our parent function, y equals x. Now we are going to have a new function, and we're going to have it be y equals -x. All right, well, our y-intercept is still the same, 0, 0, correct? So now we want to take the new slope from this y-intercept. So we're going to go down 1 over 1, down 1 over 1, and we're essentially going to go diagonally across our grid boxes, since our slope is 1 over 1, but just in the decreasing direction. And that's going to occur going this way as well. So now we can draw our new line for our new graph. And yes, it does look like it has been reflected about our y-axis. Now, it doesn't have to be from the parent function. And this is what this last example here shows. Okay, so what we have the graph of here is, this is the graph of y equals 3/5 x plus 4. Okay? What I want to find out is, what does it look like if we do a reflected function where we just change the sign of our slope and make it -3/5, and the rest of the function remains the same? Well, we would expect it to reflect across the y-axis. So let us start from our y-axis, or our y-intercept, and let's do our new slope. So we have -3, 5, so we're going to go down 3 and over 5. 1, 2, 3, 4, 5. Down 3, over 5. 1, 2, 3, 4, 5. Down 3, over 5. 1, 2, 3, 4, 5. And we can go the other direction. Up 3, back 5. 1, 2, 3, 4, 5. Up 3, 1, 2, 3, 4, 5, backwards, and finally up 3 and backwards 5. Now if we were to plot a line along those points that were plotted, we end up with a line that looks like it was reflected across the y-axis. And in both of these cases, I'm not going to write it twice, but in both of these cases, you can describe the graph as being reflected across the y-axis. This description would hold for both of these. Now let's talk about what happens when we are solving a system of linear equations by graphing. Okay, so we're going to continue to use our graphing skills here, and we are going to solve a system of linear equations. We are going to find out what the solution is by graphing. Okay, so there are three types of solutions that you can have. You can either have no solutions, one solution, or infinitely many solutions. In the case where you have no solutions, you would have parallel lines. Parallel lines mean that they will never cross. So your lines would look very much like this. Two lines that are never going to cross. This would be a case where you have no solutions. In a case where you have one solution, you would have intersecting lines. And in this case, you would have lines that cross each other, very much like this. And at that point where they cross would be the solution. And finally, you can have infinitely many solutions. And if this is the case, it means that you have the same line. So this is what it means. It means we have one line here, and I were to draw essentially the same line on top of itself. You have the same line. They're just on top of each other. Okay? So how would you find this in an equation? How can we describe this in terms of our slope and our y-intercept? Well, if you have no solutions, you have parallel lines, then you have the same slope, which makes sense because parallel lines would be increasing or decreasing at the same rate, but you would have a different y-intercept. Okay? For one solution, you would have different slopes. So if you have two equations and the slopes are different, then you know that you're going to have one solution. And then if you have infinitely many solutions, it means you have the same slope and the same y-intercept, which makes sense here again because it's the same line. You would expect the same line to have the same slope and the same y-intercept. So let's look at some examples. We are going to graph the equations y equals x minus 4 and x plus 1/2 y equals 5/2 to find the solution of the system of equations. Well, here's the first thing we need to do. The first equation's okay. We can pull our slope, which is 1, and our y-intercept, which is -4. But the other equation is in standard form. It's not in a form where we can find what our slope is, so we need to rewrite that one. So I'm going to come over here, and I'm going to write this equation, and we are going to solve it in terms of y to get it in slope-intercept form. So, to get y by itself, we are going to subtract x from each side. So that leaves us with 1/2 y on this side. And I'm going to lead with our x term on the other side because we want it in slope-intercept form. So that means our x term needs to be first. And then to get rid of the 1/2, we're going to simply multiply each side by 2. So we're left with y here If we multiply this by 2, we get negative 2x, and then we have plus 5 when we multiply 5 halves by 2. So now we have both of our equations in slope-intercept form. We can use these two equations to create our graphs. So let's do that. So in the first equation, our y-intercept is negative 4. So we're going to come down here, 1, 2, 3, 4, down on the y-axis. And then on the slope, we have 1, which means we're going to be going diagonally through all of the boxes on our grid. And so our graph is going to look like this. Okay, now let's plot the other y-intercept. So our other y-intercept is 5. So we come up here, 1, 2, 3, 4, 5. And then we're going to use our slope, which is negative 2. So negative 2 over 1, which would be our rise over run. So we're going to come down 2 and go over 1. Down 2 over 1, down 2 over 1. And so we're just going to plot that. And it's going to look something like this. And now we have two lines that cross each other. So we have one solution. And to find that solution, all we have to do is go over. So one other thing that I think is also a good idea is to label your graphs. So let's do that. This graph was y equals x minus 4. In this one, we're going to go ahead and label it using our slope-intercept form, 2x plus 5. Or minus 2x plus 5. Okay, where the graphs cross, that's going to be our solution. So we have 1, 2, 3 on the x-axis, down 1 on the y-axis. So our solution here is 3, negative 1. And this is the point in which they cross. So this is how you would write your solution. The solution is (3, negative 1). And this is what you would write, is a set of ordered pairs, or an ordered pair. Now you can check this if you want to see if the answer is correct, because sometimes things can go a little wonky when you're graphing things. So if you want to check to make sure that that is the correct answer, all you have to do is take your two equations. So I'm going to write them here. And let's substitute in our values for y and x. So y is negative 1, x is 3, 3 minus 4 is negative 1. So over on this side, we're good. Okay? How about on the other equation? Well, y is negative 1, our x is 3. So negative 2 times 3 is negative 6, plus 5 would give us negative 1. And again, yes, negative 1 times negative 1 is indeed a true statement. So we have a check here as well. So we are good. Okay, let's do another one. Let's graph the equations. X plus y equals 3 and x plus y equals 9. Then determine the number of solutions to the systems of equations. So let's start off by doing our graphs. Well, to do our graphs, we have to get both of these into slope-intercept form. Thankfully, it's a pretty straightforward process. So the first graph is x plus y equals 3. Well, if we want to get y by itself, we simply subtract x from each side, and we want to lead with x because that puts it in slope-intercept form. Now the other one is x plus y equals 9. Again, move x to the other side by subtracting, and we have y equals negative x plus 9. Well, we have the same slope, but different y-intercepts. So think for a moment as to what you would expect to happen. Well, what we would expect to happen is to have parallel lines because they're the same slope. But let's go ahead and graph it to see what happens. Okay, because they do ask us to do the graph. So the first line is, or the first equation, the y-intercept is 3. So we're going to go up to 3, and then we are going to plot our line going through the y-intercept using our slope of negative 1. Okay, making sure I have it going through correctly. And then our second slope, or our second y-intercept, is 9. So we have 3, 4, 5, 6, 7, 8, 9. We're plotting that on the y-axis. And now we're going to plot our line. And this line goes through as such. With a slope of negative 1, we're going over 1 and down 1, over 1 and down 1. And yes, we do have two parallel lines. So, since we have parallel lines, we have the same slope but different y-intercepts. So, parallel lines, same slope, different y-intercepts, which means we have no solutions, which again makes sense, right? If they're parallel and they never cross, we're never going to have a solution. Okay, now let's go to another example. In this one, we are going to graph these two equations and determine the number of solutions. Well, again, let's rewrite these so that they are in slope-intercept form. And we do that by getting y by itself. So for the first equation, we've got 2x plus y equals 3. We subtract 2x from each side, and we get y equals negative 2x plus 3. Then we go to the other equation. We get 4x plus 2y equals 6. Well, we subtract 4x from each side. That gives us 2y equals negative 4x plus 6. And then we divide each side by 2. That gives us negative 2x plus 3. And lo and behold, we have two equations that are exactly the same. So even though they did not look the same initially, this is actually the same graph. So for those of you who do not like drawing as much, the good news here is you only have one line to draw. Our y-intercept is 3. Our slope is negative 2. So we're going to go down 2 and over 1, down 2 and over 1, down 2 and over 1, so on and so forth. And I'm just going to go ahead and plot a point over here. And we're going to go up and back 1, up 2, back 1, up 2, back 1, up 2, back 1, up 2, back 1, just until we get to the edges of our graph. And we are going to draw our graph, the line of our graph through. And this is the graph for y equals negative 2x plus 3. And since this is essentially the same graph, you just have one laying on top of each other. You have the same line, which means you have the same slope, and you have the same y-intercept. So therefore, you have infinitely many solutions. Okay, so that's how you solve using graphs. But sometimes it's not convenient to always use graphs. So let's use another method. Let's use one where we don't have to graph things. Let's just work with the equations. So now we are going to solve a system of linear equations by substitution. So here are your steps for success. I list them out for you. This is what you're going to do. It'll make more sense as we do the examples, but I wanted to at least lay out what the steps are. And let's just discuss what these steps are very briefly. First, you want to solve for one variable in at least one equation, if necessary. Okay, so you want to solve for either x or y. Then, what you want to do is take whatever that x and y equals and substitute that into the other equation for that variable. Then you're going to solve that equation to get the value of the variable that is left over. And then once you find a value for that variable, you're going to plug that into one of the two equations so that you can solve for the other variable. And then you're going to write your final answer as an ordered pair. So, just listening to that probably doesn't make a whole lot of sense right off. It makes more sense as we do it as an example, so that's what we're going to do here. So we are going to use substitution. Let's get this to where you can see it. Let's use substitution to solve the system of equations x plus 6y equals 1 and 3x minus 10y equals 31. Well, first of all, let's solve the first equation for x. And the reason I want to go to the first equation here is because x is kind of by itself already. And it's very simple to get x by itself on one side, since it is already sort of by itself to begin out with. So we're going to write that first equation down, because all we have to do is move 6y to the other side, and we're done with this step. X equals 1 minus 6y. So now, we're going to substitute 1 minus 6y for x in the second equation. So let's write down the second equation. 3x minus 10y equals 31. Okay, let's now take what we found for x and let's plug it in. Okay, all I did was plug what that value for x was in step 1. I just substituted it in for x in that second equation. And that's all we have to do for the second step. Now on to the third step. Now all we're left with are two y terms. Okay? Those y terms can be combined eventually, and we can solve for that, what y is. So we can actually now find what the value for y is. So let's start off by distributing this 3. So we've got 3 times 1, which is 3. 3 times negative 6y, which is negative 18y. And then we have minus 10y equals 31. Let's combine our y terms. So this gives us 3 minus 28y equals 31. Subtract 3 from each side. So negative 28y equals, if we subtract 3 from 31, that gives us 28. And that's convenient because 28 divided by negative 28 leaves us with negative 1. So that's our value for y. Now we just need to find what x is. So we can substitute negative 1 in for y in either of the original equations. It doesn't really matter. But since we were just working with this one, let's go back to the other equation, because the other equation's already solved for x, right? So let's just take where we left off on the other equation, and let's just finish off finding what x is by substituting negative 1 in for y. When we do that, we're going to find, when we multiply negative 6 times negative 1, we're going to get a plus 6. and 1 plus 6 equals 7. So we have -1 for y, 7 for x. The only thing left to do is to write our final answer as an ordered pair. 7, -1. And we are done. So for those two equations that we were presented with initially, there is one solution, and that solution is 7, -1. So if we were to plot the two lines, 7, -1 would be the point in which the two lines cross. All right, moving on to another example of this. Let's use substitution to solve this system of equations. So, let's solve the first equation for y. So we have 3/2 x minus y equals 3. Well, we can subtract 3/2 x from each side. And then when we multiply each side by -1, we get y equals, and I'm going to go ahead and swap the order here, because -1 times -3/2 x is positive 3/2 x, and then -1 times 3 is -3. I like to lead with my positive term whenever I can. Now we're going to substitute 3/2 x minus 3 in for y in our second equation. So our second equation is 3x minus 2y equals 12. So we are going to now take what we found for y and substitute it in. So we have 3x minus 2 times 3/2 x minus 3, and that's equal to 12. That's all we have to do for that step. Now we're going to solve for the value of x. So when we solve for the value of x and see what we get. Okay, so now we're going to solve for x. We've got 3x minus, so we've got to remember that this minus 2 goes to this first term. This minus 2 also goes to the second term. Okay, so let's apply it to the first term first. -2 times 3/2 x gives you -3x. -2 times -3, well, that's going to give you +6. And that's equal to 12. Well, you're probably starting to notice a problem that's going to happen. We have 3x minus 3x. So that leaves us with 6 equals 12. Well, that is not a true statement. So here's the conclusion that we can draw from this. If you ever run into the case where you're solving for one of your variables and you end up with a false statement like the one we have here, you can say that the statement 6 equals 12 is false, and therefore we have no solutions. Now, if you want to do a check on this, just to back up what you found here, you can rewrite both equations in slope-intercept form. Okay, so let's go back up to the first equation. Well, the first equation we already wrote in slope-intercept form when we solved it for y. So let's write that here. Y equals 3/2 x minus 3. Well, the other equation was 3x minus 2y equals 12. Well, let's solve this one for y. So you have minus 2y equals -3x plus 12. And then y equals 3/2 x, because we're dividing by 2 now, or -2 I should say, minus 12 divided by -2 gives you -6. And so what we have here is we have two equations with the same slope, but different y-intercepts, which means that we have parallel lines and no solutions. All right, so let's move on to one more example of this before we move on to our next method. So use substitution to solve this system of equations that we have presented here. All right, so the second equation is already solved for y. So we're just going to write that here. So now let's substitute 2x plus 2 in for y on the first equation. So our first equation is negative 4x plus 2y equals 4. And we're going to take negative 4x here, that doesn't change, plus 2. And we're going to substitute in for y what we had in our other equation. And that's it for that step. Now let's solve for the value of x. So we've got negative 4x. And then you have 2 times 2x, which is 4x. You have 2 times 2, which is 4. And this is all equal to 4. Your negative 4x and positive 4x cancel. And so you end up with 4 equals 4. Well, we're out of variables. We can't solve for our variables again. But we do have a 4 equals 4 statement. And this time, the statement 4 equals 4 is true. This means that we have infinitely many solutions. Okay, so we have either solving for x and y, we end up with a value where the lines cross, or ordered pair where the lines cross, we have a value for x and a value for y. Or we have a false statement that tells us that there are no solutions, or we have a true statement like the one here that tells us we have infinitely many solutions. And we can rewrite both equations in slope-intercept form to perform our check. So let's do that. So the first one is negative 4x plus 2y equals 4. The second one's already in slope-intercept form. So we would expect, once we solve for y on the first one, that this is what we would get as our solution. So let's solve for y. Well, we have 2y. Adding 4x to each side, we get 4x plus 4. And then dividing everything by 2, we get 2x plus 2. And yes, they are the same equations. So same slope, same y-intercept, therefore we have infinitely many solutions. Okay, let's move on now to solving a system of linear equations by elimination. Because substitution is good and all, but sometimes we can find faster ways to do things. And a lot of times math is about finding the most efficient and easiest way to do things because we don't want to go through more pain than we have to. So let's look at this and how it works. So this one has 4 steps to success. 1, write the system so that the like terms are aligned. So you're going to line up vertically your x terms, your y terms, and then your number on the end. You're going to eliminate one of the variables and solve for the other. Then substitute the value of the variable that you solved for into one of the 2 equations to find your other variable. And then you'll write your final answer as an ordered pair. So, as before, let's do an example to see how this works. So, this example, we want to use elimination to solve for the system of equations that are presented here. So the first thing we want to do is write the equations in a stacked manner. So we've got x minus 4y equals 6. And then our other equation is 3x plus 4y equals 10. So what we're going to do is we're going to just directly add these equations together. And when we do, x plus 3x equals 4x. Negative 4y plus 4y cancel each other. And then 6 plus 10 is 16. And then we divide each side by 4. And we end up getting x equals 4. The thing that you want to look for to see if you can do elimination is you want to see if you have two variables that have the same coefficients. So two y's have the same number in front of them, 4. Even though one's negative and one's positive, you can add them together to eliminate them. Okay? So now that we have x equals 4, we're going to pick one of the two equations to plug that back into. I typically like to look for the equation that looks easier to work with. So between these two equations, I'm going to choose the first one because it looks easier to work with. There's nothing wrong with trying to find the easier way to go. So we're going to plug in 4 for x, and then solve for y. So we subtract 4 from each side, and then we divide by negative 4, and that gives us y equals negative 1/2. And then you're going to write down your solution as 4, negative 1/2, a set of ordered pairs. Okay, let's do another example, and let's start working in some word problems. So in this example, we're asked to find two numbers. The sum of the two numbers is 42, and their difference is 6. So when we're doing word problems, it's a good idea to define what our variables are going to be. So we're working with two numbers. So if we know we're working with two numbers, chances are one's going to be a bigger number, one's going to be a smaller number. So let's let x equal the greater number, or the bigger number. Okay, and then let's let y equal the lesser number, or the smaller of the two numbers. All right, so it says the sum of the two numbers is 42. Okay, well that's pretty easy. That means x plus y equals 42. And their difference is 6. So we're going to subtract the two numbers. So since we have a positive number as our outcome, that's going to be equal 6, we want to put our greater number first so that the greater number minus the smaller number gives us a positive number, that being 6. Okay, well I've got these stacked already, so let's go ahead and just put a plus here. And we're going to add these two equations. So x plus x is 2x. Y plus negative y is 0. And 42 plus 6 gives us 48. And divide each side by 2, you get x equals 24. All right, so now we have one of our two numbers. Let's find our other number. So we can plug 42 into one of the other two equations. It doesn't matter which one you choose. Here I'm going to choose x plus y equals 42. And let's put in 24 for x. And subtract each side by 24. And you're going to end up with y equals 18. In this case, we're not going to write the answer as an ordered pair because this is a word problem. It doesn't ask for what's x and what's y. We just arbitrarily defined what x and y were. So, since this is a word problem, it makes sense that we give a word answer to give context to that answer. So, it doesn't have to be anything fancy. It can be something just as simple as saying that the numbers are 24 and 18. And if you want to say the numbers are 18 and 24, That's perfectly fine. It doesn't say which one you need to say first. Okay, that's a little introduction to word problems. We'll do a couple more here in a moment, but let's do this example. Let's use elimination to solve the system of equations that's presented here. Well, we've got 4y's in here, so elimination does seem to be a good method. So let's stack the equations. And we've got negative 2x plus 4y equals 8. All right. Well, if we add these equations, it doesn't really get us anywhere, because even though we have 2 4's in front of the y's, they're both plus. And if we were to add these equations together, we would just get 8y for this. We'd have something with x as well. In fact, it'd be just x. So it doesn't really get us anywhere. But we can subtract the equations from each other. And when we do that, it will allow us to eliminate the y terms. So let's take a look at what we would end up with if we were to subtract. 3x minus negative 2x, that's 3x plus 2x, so that gives us 5x. Our 4y's cancel, because 4y minus 4y is 0. And then 18 minus 8 is 10. Divide each side by 5, and you have x equals 2. Now we're going to substitute 2 into one of our 2 equations. Let's just use the second one. So we're going to substitute that in for x. Negative 2 times 2 is negative 4. If we add 4 to each side, that'll get rid of the negative 4 on the left-hand side. And 4, when divided on each side, gives us y equals 3. So this one was just a generic problem asking us to solve the system. So we will write our final answer as the ordered pair 2, 3. Okay, so now let's move on to a couple of more word problem examples. Oh boy, we've got a little paragraph. So the key to word problems here is you want to kind of pick out what is being told to you. Okay, and let's take this sentence by sentence. So, Jennifer's school is selling tickets to a play. All right, well, there's no math in that sentence, so it's just setting up what's happening in the word problem. Okay, so we can kind of discard that sentence. Jennifer's selling tickets to a play. Good for Jennifer. All right, let's move on to the next sentence. On the first day of ticket sales, the school sold 3 senior citizen tickets and 12 child tickets for a total of $84. Okay, so we know what happened the first day. We sold a total of 84. It sounds like we're going to have something as equals to 84. And we know we've got 2 things going, senior citizen and child tickets. Okay, so it sounds like we're starting to get some variables out of here. The school took in $76 on the second day by selling 10 senior citizen tickets and 6 child tickets. Okay, so it sounds like those 2 sentences are going to be our 2 equations. All right, finally, what is the price each of 1 senior citizen ticket and 1 child ticket? Okay, that keys us into what our variables are going to be. So let's let x equal the price of a senior citizen ticket, so price of a senior ticket, and let's let y equal the price of a child ticket. Okay, we've got some variables to work with now. That's what we need to find out. That's what we don't know. So let's start off by making our equations. Okay, so in the first sentence here of the 2 sentences that our equations are going to come out of, the first day of ticket sales, the school sold 3 senior citizen tickets and 12 child tickets. Okay, so we've got 3 times the price of a senior citizen ticket. That tells us how much money we made out of a senior citizen ticket. And we have 12 child tickets. So 12 times the price of a child ticket tells us how much money we made selling child tickets. And altogether, we made $84. And for the sake of the equations, I'm just going to drop the dollar sign for now. All right. Let's do the same thing for the second sentence. The school took in $76 on the second day, so that's our total amount. And they sold 10 senior citizen tickets. So the price of our senior citizen tickets, the amount we brought in was 10x. And then 6 child tickets. So 6 tickets times the cost of those tickets each. And that gives us our total for each of the 2 days. And that gives us our 2 equations that we can solve for. Now we can use those equations to figure out how much one senior citizen ticket costs, which is our x, and how much one child ticket costs, which is our y, and that's what they're asking for. Well, we want to use elimination because that's the easier method, and that's what we've been doing. But if you look at these 2 equations, well, 3 and 10 aren't the same, 12 and 6 aren't the same. How can we do this? Well, we can do this by upscaling one of the 2 equations. That's the term I like to use for this. We're going to basically multiply each side of one of the equations by the same value, which doesn't change the equation, it just changes how it looks to allow us to do elimination. And we're going to do that to the second one. So let's go ahead and write down the first one, because now we're going to stack these things. 3x plus 12y equals 84. So what we're going to do with the second equation is we're going to multiply each side by 2. So if we multiply each side by 2, we're essentially multiplying each term by 2. So 10x times 2 gives us 20x. 6y times 2 gives us 12y. And 76 times 2 gives us 152. All right, so now we have a 12y and a 12y. They have the same sign, so we're going to subtract them so that we can get our y's to cancel. And when we do this, we're going to end up with 3 minus 20x, or 3x minus 20x, which gives us negative 17x. 12y minus 12y is 0, and 84 minus 152 is negative 68. And then we divide each side by negative 17, and you get x equals 4. Now, let's go back and substitute this into one of the original equations. Let's just choose the first one. So we have 3x plus 12y equals 84. And we have x equals 4. So we've got 3 times 4 plus 12y equals 84. 3 times 4 is 12. Subtract 12 from each side, you get 12y equals 72. And 72 divided by 12 is 6. So now we have x equals 4 and y equals 6. Remember, we're not going to write this as an ordered pair because this is a word problem. So we need to give some context. And so we write our answer this way. Senior citizen tickets cost $4 each. And child tickets cost $6 each. And that's how we would write our answer. Okay, let's take it up just a little bit of a notch with example 11. We're going to be talking a little bit more about money here. Okay? So Sam spent $24.75 to buy 12 flowers for his mother. The bouquet contained roses and daisies. The roses cost $2.50 each, and the daisies cost $1.75 each. How many of each type of flower did Sam buy? Okay, well, we can define our variables. So far we've been using x and y, but you don't have to use x and y. Let's use something that reminds us of what the variables stand for. So why not let r equal the number of roses? And let's let d equal the number of daisies. So let's set up our system of equations this way. Okay, so we know that he spent a total of $24.75. So that kind of keys us in that we're going to have one of our equations equals $24.75. All right, well, if the roses cost $2.50 each, we know that he bought some number of them at that price. So we can say that he spent $2.50 each on however many roses he bought. So we multiply it by the number of roses, which is R. Then we do the same for daisies. They cost $1.75 each. And he bought some number of them, so we multiply that cost for each daisy by the number of daisies he bought, which is D. That's our first equation. Our second equation is even easier to build because we know he bought 12 flowers in total. And so however many roses plus however many daisies he bought together make 12. So R plus D equals 12. Okay, well, if we want to use elimination, we're going to have to upscale one of these two equations. I vote to upscale the second equation. Okay? The reason I wanted to upscale the second equation is because it's easier to work with. We've got a lot of decimals going in that first equation. So why not work with the second equation if we have to do something? Let's multiply each of these terms in the second equation by $2.50 so we can eliminate our R variable. Okay? So we're going to start with $2.50 times R plus 175 times D equals 24.75. Okay, that's our first equation. We're not touching that one. And now let's multiply our second equation by 250. And let me get this erased. There we go. All right, so we're going to multiply our second equation by 250. So we have 250R plus 250D. And that's going to equal so let's see, we've got 12 times 250. Well, we know that 12 times 2 is 24, and we know that 12 times 0.5 is 6, so 24 plus 6 equals 30. And if you need to use a calculator for that, you can as well. Okay, so now let us subtract these two because we have 250R and a 250R, but they are the same sign. So we're going to subtract them so that we can eliminate them. Okay? And so 250 minus 250, that's 0. 175 minus 250D, that's going to give us negative 75 cents D. And then we've got 24.75 minus 30, which is going to give us, it's going to give us negative 5.25. Now, before we move on, let's think about this for a moment. would you expect to have a whole number to be the answer? And the answer to that should be yes. Because remember, R is the number of roses, D is the number of daisies. We can only have a whole number of roses or daisies, okay? You're not going to be giving half of a daisy and half of a rose out or anything like that. And as it turns out, when we divide each side by negative 0.75, we get that D equals 7. And then we just simply go to our other equation, R plus D equals 12, because that's the simpler of the two equations to work with. And then we're going to plug in 7 for D. So we're going to have R plus 7 equals 12. So R equals 12 minus 7, which is 5. And so we're going to end with just a simple sentence to wrap this up, because this is a word problem. So we're going to put our answer like this. Sam bought 5 roses and 7 daisies. And that's all you need to say. And if you want to say the daisies part first, that's perfectly fine. You can say Sam bought 7 daisies and 5 roses. Now let's move on to the final section of this portion of notes, and that is graphing and solving a system of linear inequalities. So we're going to return to doing a little bit of graphing here to wrap up this section. So for your steps to success, first you want to solve the inequality for y. Then you want to graph the boundary line, and you're going to graph it very much like what we've been doing with graphing lines already, except you're going to use a solid line for less than or equal to, or greater than or equal to, or a dashed line for less than or greater than. And then you're going to shade the half plane above the line if y is greater than or equal to. You'll shade the half plane below the line for y is less than or equal to, and then you can check your answer. So here's visually what I just described here. You have a solid boundary line if you are including the line, which means you have an equals to portion on your inequality. If you do not have the equals to portion on your inequality, that's displayed here on the bottom graph, then you're going to use a dashed boundary indicating that you're not including the points along the line. Now, if you are going to be including or graphing the points that are above the boundary line, as indicated by greater than or equals to, you're going to shade above the line, okay? If you are including the points below the boundary line, as indicated by less than or equal to, you're going to shade below the boundary line. So let's do a couple of examples to see how this works. So here in example 12, we are going to graph the system of linear inequalities and describe the solutions. So we are given 2 linear inequalities, and they are already nicely placed in a form that is slope-intercept form. They just have an inequality now instead of an equal sign. Okay, so here's what we're going to do. We are going to first take a look at the first equation, and we're going to plot what our y-intercept is. Okay, so in this first equation, our y-intercept is -3. So we're going to go down to -3 and place our point. Then we are going to do our slope. Well, our slope is 2. So that means our rise is 2, our run is 1. Up 2 over 1, up 2 over 1. And we're going to plot that all the way through. And then we're going to plot our line that goes with it. So this is what it's going to look like. And you'll notice that I'm using a dashed line. And the reason I'm using a dashed line is because we are not including the points along that line because we do not have an equals portion on this inequality. Okay, it's just less than. There's no equals to. All right, let's take a look at our other line. So our other line, we are going to have a y-intercept of 2, but our slope is going to be the same. And so our line is going to look like this when we graph it. Okay? Well, now we have our two boundary lines graphed. And again, it's a good idea to label which graph's which because we need to know which graph is which for this next part. So the first line is here. This is our y is less than 2x minus 3. And this graph over here is our y is greater than 2x plus 2. Well, if we're going to shade the areas that are below 2x minus 3, because we have less than, so we want to do the areas below, it would include everything that is here, okay? So we would essentially be shading everything that is in this area, okay? Now, we wouldn't do this right off because we're trying to figure out what area would be shaded in the system. But I'm just showing you the area that would be shaded for this one particular line, okay? Everything that's on this side. For the other one, we're doing everything that's greater than. So everything that would be shaded would be on this side. And again, this is only in the case if we were doing these individual lines, okay? Not the system. This is the part that you want to kind of picture in your mind, okay? Well, what area do these two graphs have in common, or what do they share? Well, for this graph, we shaded everything that was below. For this graph, we shaded everything that was above. But the two graphs did not share a common shaded area. There was not an area that we shaded for both. So in this case, we would shade nothing, because there was no common shaded area between the two. Also, we are not including the lines themselves as well. So in this case, this system has no solution. Okay, let's move on to another example. Let's see if we can see what an example that actually does have a solution looks like. So here's example 13. Graph the system of linear inequalities and describe the solutions. So we have y is greater than x minus 3, y is less than or equal to x plus 1. So let's start by graphing the first one. So our y-intercept is negative 3. So we're going to go down 3 on the y-axis, and that's our y-intercept. Now we want to graph our line, and it's going to be a dashed line again because there is no equals to portion of the inequality. And this graph is going to look something like this when we figure out what the slope is, because the slope is 1, right? So rise over run, 1 over 1, which means we're basically going diagonally through all of the grid boxes. Okay? Now, let's look at the other equation. Okay, so this was the graph for y equals, or I should say, because we're doing inequalities, y is greater than x minus 3. Okay, now let's graph the other one. So our other one is y is less than or equal to x plus 1. Well, first of all, our y-intercept is 1. Our slope is also 1. So since we have an equals to portion on this one, we are going to pick a red line to kind of go with it, and it's going to be solid. Okay? And the slope again is 1, so we're going to go diagonally through all of the boxes, and your graph is going to end up looking like this. Okay, so let's talk about the shaded areas. Okay, and let's kind of visually look at this again. So I'm going to pick a thick marker here, and we are going to start off with the first graph. Okay, y is greater than x minus 3. Well, if we're shading everything that is above, because we're greater than, we're shading above this blue line, then we're including everything that is up here. Okay, everything that is up here in this portion of the graph, and it extends above the red line, okay? Because it's everything that's above the blue line. Okay, so this is the area that would be shaded. This is just what we want to keep in mind, okay? So this blue area does include what's between the red and the blue lines, okay? Between the first and the second equations or inequalities, okay? This is something to keep in mind. Remember where the blue shaded area was, because I'm going to take it away now. Now, let's look at our red line, which, by the way, was the equation y is less than or equal to x plus 1. Let's look at the area that would be shaded for that. Well, since we're less than or equal to, it would include everything that's below the line, which would encompass our line of our other equation. So this is everywhere that would be shaded for this one individually. Okay? Well, this too includes all the area that was between the two lines. So now that we've seen what both look like, we can go in and do our final shading, which would be everything that is between our two lines. And that shaded region would be our solutions. So the solutions are all points between the parallel lines and on the solid lines. Or I should just say on the solid line, since there's only one of them. Okay, let's do one final example to wrap this up. Graph the system of linear inequalities and describe the solutions. Okay, so like before, we're going to start off by graphing our lines. So our first equation is y is less than or equal to, or I should say our first inequality is y is less than or equal to negative 2x minus 9. So minus 9 is our y-intercept, so 1, 2, 3, 4, 5, 6, 7, 8, 9. And there we are right here. And our slope is negative 2. So we are going to draw a solid line, since we have an equals to portion of the inequality. And it's going to look something like this. Okay, Now, let's label that. This one is y is less than or equal to negative 2x minus 9. And let's graph our other one. So let's use red for the other one. Okay? And when we graph the other one, we're going to start with our y-intercept. So 1, 2, 3, 4, 5, 6, 7. And we are going to draw our line through like we did on the other one with our slope being negative 2. So again, we are going to expect parallel lines. Okay? So now, let's label this one. Y is less than or equal to negative 2x plus 7. And let's figure out what's going to be shaded. Well, for the first one, we're going to shade everything that is below this blue line. Okay, so that would include everything on this left-hand side that's left of the blue line. And we, for the second one, would graph everything or shade everything that's below the red line, which would include what we just said would be for the blue line, but also what's in between. Okay? Now, here's where the difference is going to be. So the difference is that the shaded area will end up being below the blue line because that's what was shared. Because we have everything that's below the blue line according to the first equation, and we've got everything that's below the red line for the second equation, but the only area that ends up being shared is this area here that is below the blue line. So therefore, this is the area that ends up being shaded, and only that area. So here's how you can notate what the solution is. The solutions are the same as the solutions of y is less than or equal to negative 2x minus 9. Because if we graph that by itself, this is what the solutions would be, even if we didn't graph the second equation or the second inequality. So therefore, these would be our solutions for this graph. And this wraps up this section of notes. Our next section is going to be on exponents and how we can work with exponents, and that will be coming shortly.